So today we will cover some of the good stuff, basically how to get the juice out of the hardware, how to see what the performance numbers are, how to performance monitor the applications, some tools, some GUI interfaces which are pretty user friendly. Start off the morning with a demo. This was a workload done on the Cell Broadband engine by one of our tools of one of our business partners. And as I mentioned their name yesterday, RapidMind. And the reason we're showing this is because this is one real, this was demoed in several conferences, and this is one real application that you can see on crowd simulation, basically, particle simulation.
In this video, we show a demonstration program written
the person who's talking in the background is
RapidMind allows developers to take advantage of new high-performance processors, such as the Cell Broadband engine and GPUs.
So,
shown here
it
is
just
an
came into
implementation of
existence
crowd
a year
simulation
back. That's
with
a pretty new
RapidMind.
company, but
In
the
this
thing is they have already
demonstration,
demonstrated
over
support for Cell.
16,000 chickens
They
are being
have
simulated
a full
simultaneously.
system that was
Each
GA'd,
chicken looks to its
and,
neighbors
so
to
it's
decide on
available
its
for
movement.
download anytime you want to
This
play
quickly
with it.
leads to the
It's got
formation of flocks
Cell's
amongst the
backend
chickens.
support and some
Let us follow a single
optimization,
chicken in the
for
crowd.
Cell,
We'll
and they've
take over
demoed this
control
via
of the
this
chicken
workload.
to show how the other chickens react. In order to give the other chickens some incentive to follow us, we'll change our control chicken into a rooster. What makes this demo interesting is that because it was written with the RapidMind development platform, it can run unmodified on any number of high-performance parallel processors, such as the Cell, graphics processing units, or multi-core CPUs. The developer of this application did not have to know anything about these processors while writing the program. In fact, the basic algorithm for the simulation was written in a single day. We can vary how the chickens react by changing some basic parameters used in the simulation. Let's save our rooster by making the chickens more scared of one another. The change we've made to the chicken behavior quickly has a drastic effect on the overall shape of all the chickens. By zooming out to see the entire pen, we can watch how the chickens spread out. To mimic an online gaming environment, the simulation is computed on a server separate from the graphical client. The client can view one of 4 zones, all of which are computed simultaneously by the server. Note that both the server-side simulation and the client-side display were implemented using standard C++ with the RapidMind development platform. Our platform integrates directly with C++, allowing developers to use their existing C++ skills and tools. For more information on RapidMind, please visit our website at www.rapidmind.net.
The other demo that we have is on medical imaging. The comparison of a Cell solution versus a PC solution. So this is the way that the PC is rendering and reproducing the data, and that's the speed of Cell processor. So you can see that this PC solution takes 2 seconds per slice, 6 minutes to render entire volume, versus Cell, it just took 2 seconds to do the whole thing. So this was something that we demoed also in a conference in Germany, and we got pretty good feedback from all the people attending the event. So that's another demonstrated workload. All right, so let's elaborate more on the SIMD part. How do we get the performance out? This is one of the features. Now, one thing that I want to say is that it's not okay to expect that because we have 8 plus 1 9 cores, or every application will be 10-way performance. We cannot. There are some applications, if the application is not a good fit for data level parallelism, or if the application has got a lot of random memory accesses and a lot of branch that are necessary to be taken, then you won't probably even see 2x performance benefit. So it's a very certain type of applications, high performance computing, certain algorithms in HPC, certain algorithms in seismic, or certain algorithms in aerospace and defense. So it's a certain category of applications which are good for supercomputing environments are a good fit for cell. So we're not saying any or every application will definitely see a speed up. That it's possible that it will be negative speed up. So it depends from application to application. We have identified a whole lot of applications which have a lot of real world relevance and a lot of emerging technology aspects to it that have been proven to be really good scientifically when run on cell broadband engine. So this is one, SIMD programming, single instruction multiple data. How do we save on clock cycles? How do these multiple cores give us the performance benefit is what we'll cover in this presentation. So let's see. So via SIMD, we are exploiting data level parallelism. Yesterday I had gone over some things that we are operating on vectors. We're not doing so many loads, right? For 16 characters, 16 bytes of data, we're not doing the load 16 times. We are operating on vectors, we're only doing one load. That saves you 15 more cycles to go do something else. And not only that, not only just the load part, even the compute part, the arithmetic part, we don't have to do 16 additions to do computations on 16 characters or 16 bytes. We are only doing one cycle to do, be it an add or a multiply or a subtract or whatever arithmetic operation it is. We're only doing one instead of 16 cycles. You have saved time on loads, you have saved time on compute. And this is only one part of it. There's many more aspects that come together. So the SIMD concept is fully exploited on the cell processor. The SPUs are very well equipped with the power to do all kinds of vector operations. So each, as we have seen, there's 128 registers. They're all vector registers. And they are 128 bit wide, so 16 bytes in length. And you can store 4 wide full words, that is 32 bits, or half words, 8 of them, or 16 wide bytes. And again, to illustrate the simple addition point, in one cycle, we're dealing with, say, 4 integers, for example. So register A, vector A, will contain 16 bytes. That is 4 floats or 4 integers. And in one cycle, so we have already loaded 16 bytes at a time, right, or 4 integers at a time, another 4 integers at a time. And then in one cycle, we're doing 4 adds. Versus compared to a scalar architecture, what would you do? You would do A0 plus B0 equal to C0 in one cycle, right? In the next cycle, you do A1 plus B1 equals C1. The next cycle, you do A2 plus B2 equals C2. That's a normal, typical sequential program. With cell processor, or actually, with this concept of vectorizing or SIMDizing, so to say, this is also a process known as SIMDizing, is where we are trying to save on cycles everywhere. Let's pick up an example. And another concept of SIMD. So all the data are stored in 16 byte boundaries, right? Loads and stores are on 16 byte aligned, and also all accesses, all computations are on 16 byte boundaries. So let's pick up one vector, B0 through B3. It is storing 4 byte wide values. So register R1 has got B0 through B3, and R2 has got C0 through C3. Now this is one vector, and this is the second vector. We do an add, they're always aligned. So in other words, if you want to do a B0 plus C2, if you add R1 plus R2, you won't get the result in the correct location. And we'll see another example about that. But whenever you add R1 plus R2, they're always added in order. Like in other words, B0 can only be added to C0, B1 can only be added to C1, and B2 can only be added to C2. So whenever we do any computations between two vectors, they're always done in the same alignment, in the same offsets. Okay? So SIMD cross-element instructions. We have support for shifts and rotates. Permute and shuffle. So it's a similar concept, like in a traditional vector processing, you call it permute, where basically, let's pick up this register, right? So we have, whenever we load 16 bytes, if we want to just load B1, we cannot do that. It will load, want it or not, it will always load 16 bytes at a time. So we have to really find out where data is located. So data location, the offset of the data within a vector is really critical when it comes to SIMD operations. So sometimes data does not reside in the place where we want to. For example, if we want to do B0 plus, if we want to do, if we want B2 to be located in B0, right, in this slot and not over here. If we want to move things around, how do we do that? So obviously the architecture has to provide some options. Those are shifts and rotates. So you can do a rotate shift to move a byte of information to another slot. You can move 4 bytes at a time to another slot. So you can give indexes and say, okay, I want this data to be residing right here. It's particularly important in a lot of image processing applications, a lot of gaming based applications, where you want to pack and unpack values. You have RGB values. So when you're operating on a vector, in a vector fashion on RGB values, you want to apply some kind of, say, shading to all the red values, right, and all the green values and all the blue values. Once you are done doing that computation, you want to store the data as RGB, 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 and not as all reds and not as all greens and all blues, right? The image has to appear like an image and not rectangles of red and green and blue, right? So when we have to combine all these values, or even if a grayscale image, right, 0 through 255 pixels, we want to do any kind of computations. At the end of the day, you want to combine them together. That's when permute and shuffle is a very low overhead, very lightweight operation, extremely useful. So one of our goals also at the end of the day is to make sure that at least a shuffle operation, which is like a pillar, a very important concept in vector programming, is well understood by everyone. And we'll see an example of shuffle very soon. So basically, shuffle will pick up the source register, and we can set a flag like a mask. It's like, I want this byte from this register in this location. I want this byte from this register in this location. You set a mask, create a mask, and you apply it to your input data. The resultant data will be exactly in the way you want. And this is an example. So shuffle operation. So we have register VA and VB, right? And let's see. And we want the data to be located like this. So in other words, vector VA has got all these values, A0, A1, A2 in this manner. But you may be a person that, oh, I'm not that organized, right? I don't want such sequential boring data. I want some excitement. I want to move data around, right? So I want in this location, I want 1, and over here I want 4 and 8, and this is the rearrangement that you want. How do we do that? Very simply, very straightforward. Basically, we create this mask register, and we say the first byte. Now remember, these are all byte wide. So this is 4 bits, right? And this is 4 bits. So in this mask register, we create a register VT, and we initialize that register with values which basically the input register vector V1 will always be considered as 0, and input vector V2 will always be a 1. So we want to initialize this mask by saying 0, 1. That means from the 0th vector, that is the first vector, pick up the first element. From the B vector which is 1, would pick up pick up the 4th element. So in other words, pick up this value. From vector B, pick up the 8th element. So in other words, the first 4 bits will either be 0 or 1. So in real world, when you initialize the vector VT, it would look like hex. It would look like hex. 0, 1 would be the first byte. Second byte would be hex 1, 4, right? The third byte, the fourth byte would be hex 1, 0. So by observing the first 4 bits value, you find out which register am I supposed to pick up the value from. By observing the next 4 bits, you find out which value should I pick up from that register. So when we look at A6 over here, we want to say in this same location right here, in this same location, we want to pick up the value, the sixth element, the sixth byte from vector A, which is here, and place it in this location. From this vector B, we want to pick up the fifth element, B5, and put it right here. From vector B, we want to pick up 9 and put it right here. So as you define the mask byte by byte, that byte value in the same location will hold the resultant of which vector you're picking up from and what value you're picking up from each vector. Okay, and it's purely byte oriented, as it says. In native SIMD programming, there's intrinsics, there's instructions, as we discussed yesterday, and they look like this. SPU_add will add. If A and B are two integers, it will do 4 adds, right? Vector A will contain 4 integers at a time and vector B will contain 4 integers at a time. Data types, char, float, they all look the same as the traditional programming language. They're always aligned on 16-byte boundaries. Now if we say vector float star P, right? P is pointing to a memory location that holds 16 bytes of data. So what will P plus 1 be? It is basically you have jumped ahead another 16 bytes, right? So we have to keep that in mind. When we do, P plus plus, it's pointing to the next 16 bytes. And again, these are the instructions that we looked at yesterday. SPU_splats, what it does is it will take a value, a scalar value, and it will replicate on all the, if it's a vector float, and if you have an integer 2 and you want to initialize, you want to replicate 2 in all the 4 vector elements, 4 integer elements in one vector, it will put 2, 2, 2, 2. This is what splats does. Similarly on characters. And we have coding examples that we'll cover. This we saw yesterday. And let's pick up a simple example now. How do we do vector operations? This is a simple scalar code, right? In normal real world until now, this is how we write programs scalarly. If we have an input variable in1, input variable in2, output variable out, and the number of iterations that we want to do. So we initialize the loop like 0 through n, right? And then out1 is equals in1 into, a simple multiplication. And we run this n number of times. Now, how does cell give its power to this program? So, to start with, we convert all the input variables that are the scalar values that are coming in into vector values. So, convert, and it's as simple as that. It's just a simple typecast to convert it into vector. So, take all your scalar input values, in1, into, and out, and convert them into float, that is win1, win2, and v out, right? And now let's come to the loop. Now since all these input variables are now pointing to 4 vectors at a time, so 4 integers at a time instead of 1 integer, if we do a multiplication, do we have to run the loop 16 times or n number of times? N by 4, right? So now we have already saved some loops. Loops are extremely, even though they are highly predictable, there is still some overhead in the branch because there's at least 2 instructions. You save the current position, a branch and something, branch and save, and then you go back to where you last left. So avoiding loops is a key to is also one important key to getting performance out of applications. So we have saved on the loops. Another concept that we'll be looking at later on is instead of doing this one loop over here, we can do v out of I plus plus equals the next 4 elements. So in other words, in one loop iteration, you're doing one multiplication on 4 bytes. You can do on the next 4 bytes in the same loop, you can do another 4 multiplications. That's called loop unrolling. In which case, you'll be dividing NV by 2, another 2 times, because you're doing 2 of these operations in one loop. And that's another concept that we'll be covering. So this is how we are achieving data level parallelism. Instead of operating on one element at a time, we are operating on 4 elements at a time in one clock cycle. Here's another SIMD example. In the scalar code, we're doing I equal to 0 through 4k, increment the I, and basically we're just incrementing the destination vector, input vector. In the SIMD fashion, basically, well, first of all, you initialize, you basically create another vector and initialize it to 1 1 1 1, because what we want to do is we don't want to increment it one at a time. We want to increment 4 elements at one time. So we do sp underscore add of vdest, which is a converter, a typecast vector from destination, and then we add the value v1 to it, which consists of all ones. So in one loop, it's incrementing all the values of the arrays. Another vectorization example is over here. So if you have a 4 by 4 matrix, right, in a 4-way SIMD fashion. Now imagine, now we, instead of storing one y1 value in one vector, we're storing 4 vertices or 4 matrices, matrix values. So in this case, it's a dot product. So now we can do, what we can assume is basically each row of the matrix is one vector, right? Because there's 4 values, we can store it in one vector, assuming they're all integers or floating point data. So we can store the x values in another vector, and y value is another vector register. Multiply the row register by the in this whole row by the x vector register, and perform vector reduction in the product. Again, this is all more concepts of data level parallelism. Instead of doing one dot product at a time or one vector reduction at a time, we're doing 4 times vector reduction. And another approach to this, x vector is in a vector register, y vector is another register. You can copy the element basically into all 4 slots, just like we did the splat operation earlier. You can replicate the scalar element in all 4 element locations and create an empty vector, initialize it, replicate the scalar value in all the 4 locations, and just use that to use an SPU mul or SPU add with the input register. So different strategies of doing the same thing. And this is this is another thing, is that we can always store data in a vector across manner or a parallel array manner. In other words, say you have vertices, you have x, y, z and w vertices, right? You can how do you store it in data arrays? You can store, you can create like one vector which contains x, y, z and w. So all 16 bytes in one vector, right? So all these vectors will be a mixture of all v0 through vn vertices. Or what can be done is, in one vector you store all x values, so x0, x1, x2, x3. So there will be a list of vectors that will contain only the x values, list of vectors that contain only the y values and only the z values. So depending upon how your computation is done and the manner which is more simpler to you, you can pick your approach. So there's opportunities for loop unrolling and software pipelining, as we discussed. So what's the porting approach? Basically, first you write the SIMD program first for the PPU. It's again your preference. Sometimes you may just say, oh, I don't want to worry about writing code on the PPU and then porting it over to the SPU, right? Or what you want to do is basically just take a scalar program, convert it fully into vector and run it on the PPU, right? Use the vector instructions. And once you have the entire application running on the PPU, then observe, okay, what are the parts that I can break off as a module and send it in, put it into a thread, SPE thread, and fire off. Let that SPE do the work. So you can pick an approach that's most convenient. And when we do try to split the work into the other SPUs, you have to think about strategies, right? You may be splitting the data up into 64K chunks and sending it over to the SPU. What is the code size? Once you build the application, how much is the code size coming to? Depending upon that, you have to divide the data. Okay, I am using up 200K for my code size only. You're only left with 56K of data. So obviously there's something wrong. There's too much code and and very less room for data. Then you have to see, maybe I don't need this code to be running on the SPU. Maybe this can run on the PPU. So only the code that does hardcore computation should be offloaded to the SPU, so that there is a decent balance between the code size and the data you can send it off for computations. Let's pick another example of complex multiplication. Now this is a really good example because this gives us a real view of how to do multiplications and how to use these SPU intrinsics. So A plus IB equals C plus ID. This is something that we learned in what, fifth standard, right? Fifth or sixth. So A plus IB plus C plus into C plus ID is AC minus BD. So in this case, the B and D values are the imaginary values. So in a scalar form, normally what you would have to do is when you in your simple code, right? Your input vector is input 1, that is consisting of 2n elements. The reason it's 2n elements is because it's storing A, the real part, and the immediately following the real part is the imaginary number. So the real number and the imaginary number. So input 1 will be consisting of A0, B0, A1, B1, A2, B2, A3, B3 and so on. Input vector 2 will be consisting of C1, C0, D0, C1, D1, C2, D2, C3, D3 and so on. So they are interleaving the real and imaginary parts into the two input arrays. And similarly the resultant will be containing the real and imaginary parts interleaved fashion. So in the scalar code, this is what we do, right? AC minus BD. And we do that n number of times, right? We compute AC by multiplying the input vector of 1 into input 2 of I, right? And then compute BD, and then we do AC minus BD to compute the output array. Now let's see the hard part. This is how simple the scalar code looks like. However, it's not as efficient. So how do we make it 100 more lines but more efficient is what the RSPU code will look like. So I1, the input vector 1, will be SPU underscore shuffle of A1, A2 and I perm vector. So let's understand this step. This is how the input data looks like in memory, right? We're storing A1, B1 and A2, B2 in one vector, because at the most we can store how many elements in one vector if it's a 4 byte wide integer? 4, because we are having 16 bytes in one vector. So at a time we can store only 4 bytes. So in other words, we can only have A1, B1 and A2, B2 at one time in one vector. So let's pick up A1, one vector. The next vector is A2, which will be containing A3, B3. A3 is the real part, B3 is the imaginary part, and then A4 is the real part and the B4 is the imaginary part. Similarly for the second vector, B1. So this is all vector A, this is vector B. Vector A consists of A1, A2, A4, A3, A4, so on till n by 4, and B1 contains C1, D1, C2, D2, so on till by 4. So in this case, now we want to compute the sum AC. In other words, we want to multiply all the values of A with all the consecutive values of C. However, in memory they are stored as A1 and B1 and A2 and B2. So now if we multiply A1 into B1, the result will be what? A1 C1 and then B1 D1. Instead, what we want to do is we want to store all the A1 values together, and in one clock cycle we want to multiply. We want to do 4 multiplications, right? We want to multiply all the A1, A2, A3, A4 values with all the C1, C2, C3, C4 values. So now we have to create a shuffle mask. So how do we create the shuffle mask? This is the input shuffle mask. So we say 0 through 3. So pick up the first 4 bytes from the input vector 0, right, which is A1. So pick up 0 through 3, that is A1 value. Then pick up 8 through 11, which is what? A2. Imagine, right, this is what? 0 through 16, 0 through 15, A1 vector, right? This is 16 bytes. So this is 0, 3, 7 and so on till 15. This is 16 through 31, right? You get the picture? So when we say pick up 0 through 3, we're saying from the 0th vector pick up 0 through 3 bytes, right? Which is vector A1, and then 8 through 11 would be A2, and then 16 through 19. If you convert it into hex, the first 4 bits will yield a 1. So which will be vector V2. This is the second input vector. This is input vector A1 and input vector A2. So pick up 16 through 19 and then pick up 24 through 77 which is 27 which is A4. So now apply the mask and we do the shuffle operation. So SPU underscore shuffle, input vector A1, input vector A2 and then I underscore perm vector which is the shuffle mask. It's always vector unsigned char, shuffle mask. So now in our resultant vector we have all the A1, A2, A3, A4 values together. Okay. And then let's compute the result B1, D1. Now we have all the A1 values together, all the B1 values together, all the C1 values together and all the D1 values together. So now we want to compute B1, D1. So we use the NM sub instruction. Basically it will just do a multiplication and negate it. Right? And then we do a multiply add of B1 and C1, right? B2, C2, B3, C3 and B4, C4. So this is why we need to break out all the real and imaginary parts together. So we have in A2 value now, we have B1, C1 and B2, C2, B3, C3 and B4, C4. And then, so basically it's just computing stage by stage, right? What are the essential parts that we need? We need AC and BD. Okay. So you compute all these things. So we have A1, D1 and plus B1, C1 finally. One product is computed and then A1, C1 and B1, D1 also for the next I1 and I2 values. So these are the essential parts of all the whole complex multiplication arithmetic. Okay, so now we have the input vector A1, C1 and B1, D1 values, A2, C2 and B2, D2 values, A3, C3 and B3, D3 values and A4, C4 minus B4, D4. So because we computed the A1, C1 product and we computed the minus of B1, D1 product, right? We did the multiplication and the negate right here, over here. So we have these values computed. And we have the B1, D1, A1, C1 values computed. We also have the A1, D1 and the B1, C1 values computed. Now we need to store them back into the memory. So we'll create a shuffle pattern. Because the way we want to store it, the resultant vector, the way we want to store it is basically we want to put the product elements together. In other words, when we store it back in the memory, we want all the AC minus BD values, right? A0, C0 minus B0, D0 and the next one has to be what? A1, exactly. So we want to store it in the memory also like that. So that's what that is happening over here. So basically we just use the shuffle mask to our benefit and finally get the end result. And the key to observe over here, one thing to note down, and this example program is also there in the hands-on session, so when you look at the code, it all comes together better, versus a PowerPoint slide in the hands-on. We can go over it one more time. But the key to notice is that we are trying to parallelize and reduce a lot of clock cycles, is the key to understand over here. Instead of doing scalar computations n number of times, we're trying to do it n by 4, n by 8, n by 16, reduce the number of arithmetic operations.